Welcome back, and to this session where we are going to add yet another element, and this element deals with the statistical analysis of the data. So we are going to use the introduction to this statistical analysis also to remember or remind ourselves a little bit about the optimization part. So we will take a top-down approach as before, and I will show you how you can implement these things and how you can make the statistical analysis. So the overarching theme is to be able to evaluate the standard deviation in the best possible way. So when you run a Monte Carlo calculation or you do a statistical analysis of some data from experiment or from a numerical experiment or whatever kind of experimentation you've been doing, you have to provide error estimates. So if you just print the expectation value of the energy and you would try to publish that, you would get that immediately back. Because when you run a statistical calculation like the one you do with a Monte Carlo calculation, stochastic evaluation of the expectation values, you have to provide an estimate of the errors. So these resampling techniques are actually about obtaining a reliable estimate for the standard deviations, which means that we need to deal with the statistical concepts like the variance and also the covariance. And these are quantities which normally are taught in a very scattered way, unless you've taken a course in probability theory and statistics. So we will take a top-down approach first, and then we are going to go through the mathematics and the algorithms for two widely used methods. One is called the bootstrap, and the other one is called the blocking method. And then we will discuss different codes and what this means. We will also need to say something about a very important theorem in statistical analysis, which makes the foundation for the bootstrap method. And that is the so-called central limit theorem, which some of you may have encountered, but not everybody may remember exactly what it means. And that is a very important theorem because when we are going to estimate standard deviations, the central limit theorem will give us a too optimistic estimate of the error. So just for you to see what is going to come now, what we want is a reliable estimation of the errors. That means essentially the standard deviation. What we are going to use then are techniques which are called resampling techniques. So the blocking method is essentially not a resampling technique, but the bootstrap method is a resampling technique. So the bootstrap method is something you might call a poor scientist's approach to making better data. The reason for that is that often you have a limited amount of data. So typically you would have something like 1,000 to 10,000 samples. And the bootstrap method is a way to actually artificially produce more samples. The blocking method, on the other hand, is used on large data sets. And the typical application of Monte Carlo methods is one area of application of the blocking method. So when you have millions of results which you can produce, like we are doing now in the Monte Carlo sampling, that means that we could apply the blocking method to get a proper estimate of the standard deviation. And I will try to motivate why, when you calculate the standard expression for the variance, that gives a too optimistic estimate of the error. And we will see that when we are going to run the calculation. Now, I also wanted to say one thing about this blocking method, which is always fun, a fun thing when you teach. So this was actually back in, I think in 2015, and I presented the method, the blocking method, and there is an original article by two Danes, Flyvbjerg and Petersen. And Marius, who was attending the course, he had his background in statistics, so he had a bachelor degree in statistics. He was extremely dissatisfied with the theorem and the proof which was applied in the paper. And he actually revised the proof and found a better way of demonstrating the blocking method. And that actually resulted in a scientific paper and his master thesis, which was simply because he was dissatisfied with the original paper by Flyberg and Peterson. So normally when you teach, these are the things you always are hoping for. It doesn't mean that I'm going to press you guys to actually come up with a scientific paper based on this. But these are things which happen. So he had the background in statistics and was not happy with the mathematical demonstrations. This is just a small aside. So what I want to do now is to show to you the kind of top-down approach where we look at the codes and then look at what you may expect and how you should think of the coding strategy for doing the resampling. So what you will see now is again this 2-electron code, which now has all the elements which you need to bake in to your code. By the way, next week, we will say a little bit about optimization and parallelization, which will be tailored to C++, and then we'll also say something about how you can optimize with Python. So that would be a kind of technicality. And then before the Easter break, we will not introduce new topics, but we will mainly just try to work with the project and discuss that one. And again, we are always flexible with deadlines, as you know. So I just wanted to remind you quickly about this program, which you have seen many times, but where I'm adding now the statistical analysis. So if you now look at the code, this is the same code which you have seen before. So this is the 2-electron case with a Coulomb interaction between the 2 electrons, a static Coulomb interaction. The only difference now with the code, in addition to have the importance sampling, and it has the optimization where you find the optimal parameters with some few steps, then it writes every Monte Carlo measurement for every sample. It writes an expectation value to 5. So let me just run the code here and at the same time go through what it is doing, because you have seen this before. So this is now the same setup with the local energy. We have the trial wave function. This is done for the 2-electron case with a specific correlated path for the wave function. So there's nothing new here with respect to what you have seen before. There is a derivative calculation of the energy as a function of the wave function ansatz, which you have here. We have 2 parameters, alpha and beta. It calculates the quantum force. This is a function which calculates the derivative of the energy with respect to the variational parameters. So these are these 3 integrals which we have been discussing earlier in the optimization part. So there's a function which sets up the derivative, and you have seen this before. And then there's a function which calculates the energy with an input x0, which is now the set of variational parameters. So that is a vector, which in this case contains 2 parameters, which I've called alpha and beta. So you see here it's alpha and beta, and one is the first and the other is the second one in the array. It does the standard Monte Carlo sampling, but now when it calculates the energy, if I have this printout option here, it does something which will not give you necessarily the same expectation value when you take all the measurements. So what it is doing here, and this is something we can discuss a little bit. So what it does, it makes one Monte Carlo cycle. In this particular code, there is no so-called thermalization. That means that we start sampling data. In principle, what is common is that you discard some 5 to 10% of the data because you assume that the system needs to reach the most likely state, and then you start sampling. So in a sense, this is a little bit more brute force way. But what you see here is that there is a writing where we now calculate an expectation value of the energy as a function of a given number of samples. So if you run 10,000 times, what it is doing now, it is writing out the expectation value after 1 cycle, 2 cycles, 3 cycles, etc., etc. So you can obviously change this if you want to, So what you could do is actually just write the energy you observe, and then at the end, divide with the total number of Monte Carlo cycles. Then you will get exactly the same expectation values for both curves when you do the statistical analysis. We can come back to that. So here, I'm just treating every Monte Carlo cycle as an observation, and then it just writes to 5. I wanted to say a little bit more about that, because what is pretty common to do is that you write it out because if you have millions of Monte Carlo cycles, a typical run could be 1 billion. You don't print 1 billion of Monte Carlo cycles. You would typically print this every 1,000 times. So you collect the expectation value after 1,000 cycles, then you calculate the expectation value, and then you print out. So these are things which you have to decide. And you will see that there is no kind of consensus on when should you print out. So what I'm doing here is just to print out after every cycle, because I don't have so many. So the file doesn't become that large. When you're running this in parallel, you would obviously have many different outputs for the energies. So you just have to make up whether you want to calculate this without dividing by the number of cycles you've done till a certain point, or whether you want to think of everything you print out as an observation. And then when you look at this, what I'm doing first is this cheaper calculation where I place myself randomly, or it's a good guess for the initial values for the parameters alpha and beta. So the optimal value for the non-interacting case is 1, and I put it to 0.9. The optimal value for this parameter, which deals with the Coulomb interaction, is roughly 0.4, and I put it to 0.2. And this is where I typically call, and I use Broyden's method. So I use this scientific Python function, which is called minimize. That needs a function for the energy, and it needs a function for the derivative. And there is also tolerance for the convergence here. When I'm done with that, this function returns the optimal values for alpha and beta, my parameters. When I have the optimal values, then I start the big Monte Carlo calculation. Now, this blocking method, as you will see later, is most conveniently expressed in the number of observations as powers of 2, 2 as powers of n. And you will see here that the number of cycles is 2 to the power of 19. And this has to do with the fact that we are splitting the data in blocks of 2 and 2 each time. I will come back to the setup of the blocking algorithm. So then we get a final energy, and we have this output file where we write things to. Here you will see the final result. And you see now that when I've run the cheaper calculation, I get this value. This is a case where I have the exact value. And the exact value is 3 for this Hamiltonian, for the interacting case. It's one of the few cases where you can solve analytically an interacting problem. And this case is a 2-body problem. So the exact answer is 3. And you see now that the Monte Carlo calculation for 2 particles with 2 parameters in 2 dimensions is actually giving a pretty good result. Now, what is missing here is the error. So when you print something like this, you have to have plus minus the standard deviation. Because if you don't provide that, nobody will believe you. It's as simple as that. And I've had cases of Monte Carlo papers where people actually submitted for publication without providing errors. And the claim is often that the errors cannot be seen on the graphs, but then you print them in a table, because having an error estimate is essential here, especially when you're dealing with a stochastic method where the error comes for free, almost. Now, one of the things we will discuss now in a little bit more detail is what do we mean by the error? Can we just use the standard equation for the variance? So what you're going to see now is that the variance, the way we calculate it, is assuming that these are independent and identically distributed. What happens then is that this error will be too optimistic. It will actually be too small. So what you have now is a file, which in this particular case contains, as you can see here, the number of Monte Carlo cycles, 2 to the 19th observations. So the file is pretty big. Now I'm using that file as an input to this resampling analysis. And you can see now I'm just reading in this file, and this is using the bootstrap method, which I will discuss in more detail right after we've gone through the demonstration. So the bootstrap method now, what it does, it calculates a mean value, but keep in mind that this mean value will be a little bit different from this one, because I write every observation as a function of the number of cycles I did at that specific point. So in principle, you should have the same at the end, the same mean value, because the mean value should not change. Okay, just keep that in mind. So when I now run these calculations, I'm taking this data. Oops, this should not be the case. But why they didn't do it? Just a moment. I think there's some update which didn't take place. Let me just do that one, because it seems that the Python file I plugged in here didn't have an update which I needed. Yeah, I want to have this statement here. Okay. So the codes which you have here actually taken from the thesis of Marius, and he made them freely available. Now what you have here, so this is the standard deviation, the last number here. And you see that this number is something like 10 to the minus 5. So what you would do then, you would take this expectation value here and add plus minus 10 to the minus 5. Now this bootstrap method assumes that you have independent and identically distributed variables. So what you will see is that this result is a little bit too optimistic. So the error is too good. And I will try to guide you through why this is too good, actually. Now, what comes in here is just the implementation of the blocking method. So concerning the project, what we have normally told people is that there is no need for you to write your own statistical analysis codes. So these are codes which you can find in statistical packages. Actually, the statistical package in Python has the bootstrap method baked in. So these are methods which are well described in the literature. And what we provide here are just the tools by which you can make the same analysis. Now, if we run the blocking method, what you will see now is that so you obviously have the same mean error. So the two values, the two results should give you the same mean. But you see that the standard deviation now is a little bit bigger. So in this case here, you would have something roughly, this would be 10 to the 6.3 times 10 to the minus 5. It's a little bit bigger than the one which we have for the bootstrap method. So we have a standard deviation which is only slightly bigger here. So feel free to use these tools. And now we need to discuss a little bit what it means. So summing up this kind of top-down introduction to what we are doing, what you need to do is to decide on how many of these Monte Carlo samples you want to write out. So if you're running 1 billion Monte Carlo cycles, you wouldn't write out 1 billion Monte Carlo events, because that file would just become huge. You would typically print out every 1,000 cycles typically. So that means you would have 1 million data, just to give you an example. Yeah? Say again, who? Yeah, you could just do the analysis within one whole package. That's no problem. But what is often done, since many of these Monte Carlo calculations, like the cases we have, are cases you can run within few hours. But if you run a calculation of a bigger system, this can take days. And when it takes days, it's much more common that you would write to file the data you produce and then do the post-analysis afterwards. So that's pretty common, because you would often run this with a C++ or Fortran program on a high-performance computing facility. This would be tailored to that specific facility, and then you would just produce the data and then you do the post-analysis. So I hope you see the kind of overarching thing which we need to do. And then feel free to use these tools which you have, this software. You can actually, if you go to Mario's thesis or to his scientific article in PhysRev, you will find the same access to the same codes. So what I've done here is simply to use what he produced. Okay, so let's take a look at the statistical analysis and why we are dealing with these resampling techniques. So the blocking method is in a certain sense not a resampling technique. So resampling is often used to you producing vanilla data again and again and again. The bootstrap method is one of those. And for those of you who have studied, let's say, statistical data analysis and machine learning in particular, many of these things are pretty familiar. So it's not that different from what some of you have seen before, except that the novel thing would be the blocking method. So the bootstrap method we are going to discuss now is often used on data sets where you have something between 100 to 10,000 data points. If you go beyond that, it's common to use other methods. And the reason for that is simply because these other methods are actually more precise than the bootstrap method. So they are indispensable tools in the modern statistics. So typically they involve repeatedly drawing samples from a training set and refitting a model of interest on each sample so that you all can obtain some additional information about the fitted model. So one of the things you want, and this sounds like a horribly long detour, which we are taking now, because we just want a tiny quantity. We just want an estimate of the error. So you may say, why should we make that big fuss about it? Well, having a good estimate of the error is essential, because that can have important consequences for your data analysis later. So many of these methods can be computationally expensive. That is one thing. So you're often searching for a kind of compromise on how much you want to invest in CPU cycles and the precision which you want to have, or you're happy with. So the bootstrap is the one which is widely used. And the reason why you can think of this, or why we should think of these resampling methods, is that the way we are dealing with the simulations is that we can think of them as numerical experiments. And in particular, in our case, we are running a numerical experiment. Starting with a random seed, we get a specific result, and then we repeat these experiments again and again and again. And when you run a Monte Carlo calculation, the more you can perform, the more calculations you can perform, the happier we are. And Monte Carlo methods are actually the kind of excellent example par excellence. And the results can be used with the same statistical tools that we would use when you analyze experimental data. So what you're doing now wouldn't be that much different from an analysis of experimental data. An experiment can be many things. It can be a survey, or it just can be you running a specific experiments. And we obviously want to measure and find out how accurate they are. So when you do this kind of experiments, when you look at numerical calculations like the ones we are doing, you have two typical types of errors, the statistical one and the systematic one. So the systematic ones are the nasty ones, and we will not deal with anything nasty here. So nastiness means that, like the Hamiltonian, which we have, is a model, and we cannot quantify properly what's the error behind the model. So many people think often when you solve a problem with a specific Hamiltonian, that is a way to represent reality. It may not be realistic at all. So we have many academic models, which you can even find analytical solutions of, but they may have horrible systematic errors. So the things we can quantify are the statistical error. Anything else we do, method-specific errors, or the input itself, the Hamiltonian, is that the correct one or is it not? The laws of motion, are they correct? These are the systematic errors, and they are much more difficult to quantify. Okay? Unless you have experimental data, because then you can do some further statistical analysis and then say something about the estimate or the error estimate from the specific model you have chosen. That is fully possible, and that would lead you into what is called Bayesian statistics. But okay, so what I'm going to do now is switch back to the whiteboard, and we are just going to go a little bit slowly through what these different elements actually mean. So any questions so far? Things which are unclear? So the important thing is that you see what you need to have in the program. So this element is actually not that time consuming when it comes to programming, because you can use all these programs which we provide you with. But let's switch to the whiteboard here. So what we are going to deal with is something which in statistics is called non-parametric models. So have you heard about non-parametric versus parametric models? Anyone's heard of that? So the name itself should give you a kind of feeling of what it actually means. So a parametric model means that you have a model for the probability distribution defined in terms of some specific constants and variables. These models, which you have then these parameters, and these parameters may have been tuned to the data. So you have an explicit expression which allows you to calculate statistical properties. A non-parametric model means obviously that you don't have such a parameterized model. And this is often the situation which we end up with, and that leads to what in statistics is often called a frequentist approach. So what you have are the observations. And from the observations, you try to find an estimate of the mean value, the variance, standard deviations, and other statistical properties. So there is a very, very important difference. There's also another thing to think of, that even if you have a parametric model, you may not use it, simply because the parametric model has a high dimensionality. So if you think of the wave function for a 100 particle system in 3 dimensions, that means that even if you knew the wave function, you would have a model which would depend on 300 variables, 3 dimensions times 100 particles. So even if you have it, it may be too complicated to simulate from it. So in many cases, what we have are just the data. And this is normally something which would end up in the box of so-called non-parametric models. So the bootstrap and both these blocking methods, which we are going to deal with, they are examples of statistical data analysis of non-parametric models. So as I said, when there is a particular model, a mathematical one, with adjustable constants or parameters, that normally defines what's called a parametric models. And statistical models, which are based on these, are obviously called parametric. When you don't have such a model, then the statistical analysis is normally called non-parametric. And then you assume normally that the random variables are so-called independent and identically distributed. So that's a very important assumption, which we are going to use now in the derivation of the central limit theorem. Some of you may have seen it. So how many of you remember the central limit theorem? 1, 2, 3. So is it okay if we just repeat a little bit about the central limit theorem? Because this has consequences for the kind of analysis which we are going to make. So we are going to make a fundamental assumption about the data, because that is also one of the assumptions which leads to the standard bootstrap method. So if we now start with that one, the standard bootstrap, there is a so-called bootstrap method, which assumes non-IID events, but the standard one assumes that the stochastic variables and random, obviously then random variables. And let's just call them in a very generic way, X of I, are so-called IID. So to quickly remind you of that, that means that they are independent. And this is identically. And the final one here is distributed. So what it means then, when we now are looking at a specific expectation value, so let's quickly remind ourselves of some of the statistical quantities which we are interested in. So the quantities we want is obviously to have a proper estimate of the mean value. Estimators. So when I say the estimators, these are the quantities we want to calculate, and they are often called the estimators because we make an estimate of the mean value and we make an estimate of the variance. And with the variance, we calculate the standard deviation. So the estimators are typically the quantities we want, the mean value, which in our case is going to be something we will call the sample mean value, and the variance. And later today, we are going to introduce the covariance as well. And with the variance, when you take the square root of that one, that tells you about the spread around the mean value. And that is a very important quantity because that gives us a kind of feeling of how reliable our calculations are. So what we have then, just to remind you, if you have the probability distribution, and if we take the mean value, this is given by an integral of x, the domain where x is defined, and then it will be p of x, of d of x, and p of x is a probability distribution function. So I'm going to use this acronym PDF. So p of x multiplied with d of x, this quantity, p of x, d of x, represents then the probability of finding a specific event in the domain between x and x plus d of x. And these functions, if it's a continuous and nice function, is normally called a probability distribution. Alternatively, if you now have a discrete distribution, this is a continuous one, you would then have a sum over I element in this domain of events which you have. And then you would have an x of I and p of x of I. So this is in case you know the probability. But since we are using a non-parametric approach, we are just going to have the frequency of data as input. So in our case, we don't know, or even if we know it, it's too difficult to sample from it. So we don't have p of x. So what we end up with then is the sample mean. And I'm going to call this mu, and that is given by 1 divided by n. And this is defined by I equal 1 up to the number of observations of x of I. And this is normally different from E of x when n is not infinitely large. Okay, So these are some of the premises which we have. So even if we have the probability distribution, as I said, since this is often a problem with hundreds and hundreds of particles in many dimensions, then even if we have the P of X, it may be too difficult to calculate the norm. So remember now that this P of X has to be normalized. So just to quickly remind you of some basic quantities. So we have a P of X for X defined in a domain here, and this is normally normalized. And to perform that one for a multidimensional object can be too difficult. So this is the type of problems which we end up with. And that's why we typically run a stochastic evaluation of an integral, which means that we will have the values of the expectation value of the energy for a given set of values n. So that's a pretty common situation which we have to face. Now, if we then look at the variance of this quantity x, so I'm writing it like this is obviously given, and later we are going to introduce the covariance as well. This is now given by P of x, and then it's multiplied with x minus, and then we have the true expectation value of x, which is a constant here, and d of x. And if we have a discrete one, then this is just a sum over all the elements in that domain, and then we have P of x of I, and then we would have x of I minus the same quantity, but which is now evaluated for a discrete distribution. So that's the same expression. Now what we end up with is the sample variance. And the sample variance is something which I will label as a sigma squared, and that is given by 1 over n, and it has a sum over I, and again, I is now defined for this domain of events which we have, which may not be the same as the one which we had here, because this could in principle represent an infinity of observation or a huge number, whereas this number which you have here is normally a limited number. Now, you see also that the basic assumption you're making here is that you have replaced the probability. This is a very important thing just to remember. So that Px of I is equal to 1 divided by n. So this is a basic assumption we are making. And then we have Bernoulli's law of large numbers, which tells us that in the limit n goes to infinity, we should approach the correct expectation value. So this is simply x of I minus this quantity we call mu squared. So just to remind you what mu squared was, the mu is the sample mean, and that enters the sample variance. So it's common to actually have a factor of n minus 1, because mu is no longer an independent, this is sigma is no longer independent of the sample number, because this is a quantity which depends on the total number of experiments we have run. So when you apply this formula here, or you use that in NumPy, for instance, it will have a factor of 1 divided by n minus 1. But if n is large enough, you can leave out the 1. But if you calculate this for small data sets, you may get a difference if you forget to divide with 1 divided by n minus 1. So keep in mind that these are the quantities which we deal with. So we are looking at the frequency of the data, and then we want to find the best possible estimate of this. So what I'm going to do now is to introduce the bootstrap method before I talk about the central limit theorem. And then I'm going to go a little bit back and forth. So the bootstrap. Now, what we are going to do now is to assume that we can produce a new sample. So we have an original sample. This is your experiment. And the original sample is something which I will label with X, and that will contain a set of observation, X1, X2, up to some X of n. This is your sample of data, okay? So what we are going to do now is then to produce, so we assume now So we assume we can produce new samples which I'm just going to call X star, and then produce new estimates for the mean values, and produce new estimates for the mean value mu and this sigma squared. So basically, the algorithm is extremely simple. So suppose now that we produce these new samples, and then we calculate new mean values. So I'm now going to define the following quantities. I'm going to call this a theta of n with this new sampling of 1. I'm going to produce a new one, a theta of 2 of n. So n is the number of data I have in every measurement, up to some theta of b, so of n, of a resampled data, which I call for b. Then each one of these, a theta of n of I, is going to be equal to a 1 over n, where I now have a sum over j equal 1 up to n of a new resampled data of. So I here stands for the sampling which I made. So just to give you an example here, when you've written this down, what we would then have as a typical example, suppose the original data is given by this 1, 2, this is a very exciting sequence, and it tells you about my huge, massive fantasy I have in setting up examples. And then I make a new one. So I just shuffle randomly. And then I'm going to add another thing with a replacement. Because this is going to be important. So this could look like 2, 3, 3, 5, 1. So this is my new data set. Okay? So I could now reshuffle randomly, but why would it make sense to be able to pick the same value? Do you have any feeling for that? So let me give you a hint. When you run your Monte Carlo situation, do you reject the case where you stay in the same place? Do you reject it only once, or can you reject it many times and move from the same place? So you could make a run where you stay in the same position. Every one of these would be a valid measurement, okay? So when you know a resampling like this, you could think of you having measured that specific energy, and then you measure the same 2 times. So what you're doing with this kind of reshuffling is that you are producing, in a certain sense, a new data set. So this is what normally we call a poor scientist approach to the data, because it takes so much time to achieve this fancy sequence, 1, 2, 3, 4, 5. It took us months to get it. So if you're dealing with lattice QCD, which is the one way you would implement quantum chromodynamics in order to simulate the interaction between quarks and gluons, a typical run takes 3 to 4 months. And you would end up with something like 500 to 1,000 events just to produce that. So it means that your statistics is not something you would brag about. I mean, you don't have much data. And then a resampling like this can be seen as a cheap way to generate new data sets. And you can actually show, there's a proof that when you have done this enough times, this actually approaches the true expectation value and the true variance for that specific distribution if the data are identically independent and identically distributed. So after the break, we are going to run a demonstration with a bootstrap with a Gaussian distribution. And you will see then that we get the result which the central limit theorem says. So this is a very good method if you have data which are assumed to be independent and identical to you. And then the bootstrap is a kind of method of choice because it's extremely simple and you can prove that you approach the correct expressions or the correct values in this case. So what you would be doing then is that you would continue this calculation. So that means that when you then calculate the final after B resamplings, you would then have a mean value, which I write like this, which is then simply 1 over B over the sum over all the mean values of B. So we can then, so this is an estimate of the mean value. We normally call this an estimator. And then you can use that one to calculate an estimate of the variance. So we can now calculate the variance of this theta B. And that will simply be given by 1 divided by B. It's actually B minus 1, because these are not independent quantities. 1 up to B here. And then we would have the individual measurements of I minus this expectation value, the final one, but then square. So when you do this B times, so you do B reshufflings. So we do this B times. And each time you calculate the mean value. And you obtain the mean value, and with that mean value, you can go back, and then you can send back the variance in. So what I'm doing here now, when we are going to link this with a demonstration of the central limit theorem, what we are going to do then is simply to produce 1,000 or 10,000 data points using the normal distribution, and then we're going to reshuffle it 10,000 times. And then we're going to use that as a test of the central limit theorem. So we're going to run a numerical demonstration of the central limit theorem. The alternative, which you could do, instead of producing 10,000 points and do 10,000 bootstraps, would be to run the calculation 10,000 times 10,000. And that will give you 10 to the 8 data points. So for the normal distribution, this is actually faster than doing a bootstrap. But for a heavy calculation, that is definitely not the case. So what I'm going to show you after the break is that this recipe gives the same as if you were to generate 10,000 points 10,000 times with a normal distribution, or any distribution which is independent and identically distributed. And then the bootstrap then is a cheaper way of doing that set of numerical examples. Do you see the basic philosophy here? So after the break, we are going to look at the central limit theorem, and we're going to run a simple demonstration of it. And after that, we are going to prepare the ground for the blocking method, which would be the other method which we are going to, this will be the preferred method for the statistical data analysis. So it sounds like a, how to say, a long detour in order to get a tiny number. But these tiny numbers are the numbers which add to your credibility in a statistical analysis. If you don't provide it, or if you run an experiment, you will probably see, if you look at the experimental papers, if there are no error bars, nobody believes you. It's as simple as that. Actually, there's even people who would even suspect you of cheating, of hiding away the errors, if you run a real experiment. Should we take a small break? Is that fine? I hope this is not too boring, actually. It sounds like a very strange thing. Marius, who was following these lectures, got so excited that that ended up in his master thesis in a scientific paper. And actually, there are many who are using the codes he developed, which is pretty neat. Okay, I'm going to pause. So what we're going to do now is to first go through the central limit theorem so that we remind ourselves of what it actually stands for and what it means. And then we're going to look at a demonstration of it in terms of the Gaussian distribution, which we are going to study using the bootstrapping method. So the bootstrapping method is a method you can view as a cheap way of generating new samples. So let's take a look at the central limit theorem and just remember a little bit what we have. So what I'm going to assume now is that I have a set of observations. So I'm running a series of experiments. So the central limit theorem. So let's assume now that we have n experiments. And each experiment contains n observations or n events which we look at. So a typical experiment produces a mean value, and each of these have a mean value, a sample mean value. So we are going to call this an x bar of I, which is now simply a sum over n. And then we have a sum from j equal 1 up to n of this x of experiment I with a variable j. So this is a specific experiment. So suppose we make a measurement of some decay properties in nuclear physics experiments, and then we count the number of beta decays, for instance, which we observe. We do that one evening, and then we repeat that experiment the next day, the next day, the next day, and so on. So you can think of this as a series of experiments which we are running. We're also going to make an assumption now that these experiments, each quantity which we have here, is an IID. What we're also going to do now, in order to simplify the notation a little bit, so we're going to simplify notation, and I hope this is not too confusing. And I'm going to let this x of I, which you have here, I'm simply going to rewrite it as an x of I, okay? So the x's are now mean values of a given number of experiments, okay? This is simply because I don't want to carry with me all these bars over the numbers. Then, when we repeat this n time, the total mean value is something I'm going to call for z, and that is simply x1 plus x2, and then plus x of m divided by m. I'm also going to make an assumption now that these guys, which you see here, they have all the same distribution. So this could be a Gaussian, it could be a Poisson distribution, any distribution which leads to independent and identically distributed events. So this is an assumption which I will make. So we assume now that all these have the same PDF. This is one of the underlying assumptions which you have when you're looking at the bootstrap method, that all the events you have are assumed to be independent and identically distributed. So the question which we ask then is, what is the distribution of Z? So what is the distribution of Z? So that means that what we are looking after is a P of Z, which we don't know. So one way to do that is actually to set up an integral which now represents the probability of obtaining an average Z value, which is the product of obtaining arbitrary mean values, X of I, but with a constraint. So what I could do now is simply to set up an integral where we now have an integration, and these x's are in the same domain. So I have an x1 in the domain D, and I have my dx1 of px1, and then I have a new one where I have an x2 in the same domain of x2 of p. So these are the small guys here. This is the uppercase probability, and the smaller ones are the same. So this is not the same as these guys. These are all the same. And this runs all the way up to an x of m. And then I have a dx of m over px of m. But this is now multiplied with a constraint, which I'm putting in. So I have a constraint that this z should be equal to these sums of the mean values. So I have minus x1 plus x2 and plus. So this is one way by which we can construct the final distribution. So I'm looking at the product of all the individual ones. So we are, because if you think of a set of independent events, that would be the product of all the individual probability distributions. But we are having a constraint, and that constraint is that this value z has to be the mean value, the sum over all the x's divided by the number of experiments. So what we do now is that we simply replace parts of it, the Kronecker delta, with the integral representation of the delta function. So in order to find a mathematical expression for this, and I guess for those of you who are familiar with the central limit theorem, it shouldn't come as a surprise that this P of Z is going to be a Gaussian or a normal distribution, depending on how we center it. So the central limit theorem says that in the limit of m, this number of measurements goes to infinity, this distribution should approach a Gaussian if, and this is something you have to be careful with, if and only the events which we have are independent and identically distributed. If they are not, you will not get a Gaussian. So when people use the law of large numbers and distribute grades, for instance, the assumption is that all you guys are independent and identically distributed. So you can obviously question that basic assumption. And since I question that basic assumption, that's also why I refuse to normal distribute grades. Okay, anyway, that was a digression. But let's now remind ourselves of the expression for the Gaussian distribution, no, the delta function in terms of an integral. And this is something you may have seen. And this is given by 1 divided by 2 pi. And then I have an integral from minus infinity to plus infinity. And then I have a dq, and then the exponential. And this exponential then has, as argument, complex I times q. And then I have z minus, and then I have x1. So what I'm doing now is simply to set this expression up, which you may have seen before. xn. And this should be divided by n. There is a new parenthesis, and then there is a final parenthesis here. So I assume that you've seen this expression before. And then in that integral, in the integral for pz, we just insert 1. This is just a trick which allows us to perform the calculation. We insert 1, which is equal to e of I of mu q minus mu of q. And this variable mu is something which is going to be given by the integral of the probability distribution which we have, this one. So that's the mean value for each x. So remember now that these x's, in principle, what I am getting here, if you look at the integral which I have, if you look at each one of these are actually going to be equal to mu. Yeah. Oh, sorry. So it's always the same. I mean, I have it in front of my notes, it's written correctly. And then when you write it on the whiteboard or the blackboard, you always miss something. So we are humans. Okay, so let's now insert that one. And then we can, is it okay if, or maybe I should wait a little bit till you have written it? You got it? Okay. So then we can then rewrite this P of Z. And this becomes equal to 1 divided by 2 pi. There is an integral from minus infinity to plus infinity of dq of E of IQ. And I'm going to rewrite this in a specific way, C minus mu here. And this is multiplied with an integral. And now I'm just replacing all the x's with just one common variable, because these integrals are actually the same. So it's going to be written by a P of x. And then I'm going to have an exponential of IQ of mu minus x divided by m, like that. And this is all to the power of m. And you will see that when you now write this out, since all these variables, x1, x2, and so on, they are independent of each other. So just remember that. And they are independent and they have the same distribution. So we can actually rewrite this quantity as this quantity which you see here. So keep in mind also that this x of P of x is a normalized quantity. So this is equal to 1. So when we do that, what we get then, if we look at one of these integrals, so if you now take a closer look at this specific integral here of d of x, so or let me just take away the infinity signs. I don't need to define them, but normally we would assume that x goes from minus infinity to plus infinity. So we don't lose anything there. And then we have an E of Q of mu minus x divided by m. So let's look a little bit at this integral. So what we do now is we just simply Taylor expand the exponential. And when we Taylor expand the exponential, what we get then is the following. So we get an integral of x, no, sorry, P of x of d of x. And then I have 1 plus I times q of mu minus x divided by mu m. And then I get minus, and then I have q squared of mu minus x squared divided by 2m squared. So this is just Taylor expanding the denominator, the exponential. Now, if you look at these terms, so let me remind you that on this slide here. So with mu is just the integral over x, P of x, d of x, and P of x, d of x is equal to 1. If you use these properties, what does the first term give you? So if you use this, you have this term, and then what does the first term and what does the second term give you? One and 0. So what we have then is 1 plus 0, and it's obviously it has to be 0 because this is just a constant. And then I have x, and when I integrate of that one, that gives me mu, so I get mu minus mu. Now, if you look at the second term here, what does that remind you of? Say again? Yeah, but that has a name, the variance. So the second term, the third term gives us minus, and then I have this quantity q squared, so I get a sigma squared, and then I have a 2 over m squared, and then this has higher order terms here. So what's pretty common to do then is actually to rewrite this now in terms of another series. So what I'm going to do now, instead of going through all the algebra which is needed to do the integration, I'm just going to use that property so that in the limit, so when you take this limit where m goes to infinity, so I'm going to plug this expression which you have here. I will have to plug that one back in here. So there are some different integration tricks which will be applied, but I just wanted to save you for all these kind of technicalities. But what you will find is that this P of Z, which we define, is going to be equal to 1 divided by 2 pi. And then I have a sigma squared divided by m. And this is multiplied with the exponential of minus. And then I have Z minus mu squared divided by 2 sigma squared over m. And this is nothing but a standard Gaussian with a mean value mu and a variance, which is sigma squared divided by m. So this is Gaussian with mean value, mu, and variance, which is given by sigma squared divided by m. So sigma squared is the variance. Remember now that sigma squared is the variance of just one experiment. So sigma squared is given by x, and then we have p of x minus mu squared of d of x. So that's the variance of the individual experiment. And now we run m experiments. So that means that this has a standard deviation, and this is often shortened to STD, standard deviation, which is equal to sigma divided by the square root of m. And you've probably seen this many, many times. So this is essentially the central limit theorem. So the central limit theorem states that if you have independent and identically distributed variables, and you perform m experiments, then the standard deviation will approach the standard deviation of a single experiment divided by the square root of all the experiments which you run. And that's an extremely powerful result. But this applies only if you make this assumption that the x's which you started with are independent and identically distributed. So, and that is now when you can start questioning the Monte Carlo thing, because you know what, when you run a Monte Carlo calculation, your results will depend on random numbers which are not necessarily independent of each other. They are generated, they are so-called pseudo-random numbers. They normally pass the test for what we call randomness, but they are generated by a deterministic algorithm. So if you are to calculate something like the correlation function between the random numbers, that should ideally be 0, but it's normally not. So there will be some kind of dependencies from one experiment to the next one. So when we run a Monte Carlo calculation, if all the energies you calculate were independent and identically distributed, then we could actually use this formula here. But that's not the case. And that's why I say that if you were to use a bootstrap tailored to independent and identically distributed events, you will get an expectation value for the variance and thereafter the standard deviation, which is too small. Because there will be corrections coming from the so-called covariance matrix, which measures the correlations between different measurements, which is non-zero. Simply because we have data which are somewhat correlated. Now, in physics, we actually have systems which will always be correlated. So in some cases, we don't want that result because we have strong interactions. So if a system of particles does not interact, if you think of your particles in a harmonic oscillator, that would be an example of a system where the final wave function is just a product of the individual harmonic oscillator wave function. And if you square that, then you have a probability, which is the square of each individual single particle probability. That is an example of independent and identically distributed results. And in that case, calculating the variance of your measurements or whatever you do with a harmonic oscillator should give you this result. As soon as you bring in a correlation between the particles, which comes through the forces which act between them, then your wave function will no longer be the product of single particle wave functions. So that's something which is important to think of. And in physics, we are actually not interested in uncorrelated events. In physics, we want to have things which are correlated because that tells us which forces are at play. So in a sense, an uncorrelated system of independent particles doesn't do anything, essentially. And it's the action which we are interested in. So in a certain sense, the kind of data which we are going to look at, the Monte Carlo measurements which we make, they obviously, every energy reflects the fact that the particles interact, but you could think that every energy should be independent of another measurement. But that will not be the case when you run a Monte Carlo calculation, because you have a kind of linear dependency in the generation of the random numbers. So in our case, we will find that the error we produce would be too optimistically small if we just make this assumption. So there's a long detour here actually to get to the point. But I hope you see the basic reasoning here, right? Because we don't have, in essence, independent and identically distributed events. So if you use the bootstrap in its simplest form, like the one which I showed you before the break, this is exactly what will happen then. We would get this value. So let's look at a numerical demonstration. So I'm going to try to convince you that this is actually the case, what we did here. So there is an example in the Jupyter notebook here. So if you just scroll down a little bit, here's just a repetition of a lot of the statistics. But there is if you scroll down and look at the bootstrap method, so there's a jackknife, which is another method. But here we have the bootstrap itself, which we discussed before the break. And I just wanted to say what I'm doing here. So here, I'm calculating a Gaussian distribution. So I'm producing 10,000 data points. And then I have a mean value of 100, and I have a standard deviation of 15, the sigma value which you see here. So what I'm going to do now is to perform a bootstrap with 10,000 bootstraps. So that means that I'm going to take this data set which I generate, and keep in mind now that I'm using random number generators to generate the numbers, and I will have 10,000 measurements, which means that when I calculate the mean value from my distribution, I will not get 100. Just keep that in mind. Because the random number generator will only have 10,000 events, and that means that it will distribute them in something which looks like a Gaussian distribution, but it will not have enough counts for this to be a smooth continuous function, which means that when you run this code, you may not find the mean value to be 100. So I'm going to say a little bit about it. So this is the original. So I didn't get 100, okay? I also didn't get 15 for my standard deviation because I'm running an experiment with 10,000 samples. If I increase this to 1 million, you will get much closer to 100 and you will get much closer to 15, okay? But what I'm doing now, if you now look at these calculations here, I am now producing here in this function, I'm doing the bootstrap, and this round int here, that simply reshuffles my data points, which I had originally, the 10,000, it reshuffles it randomly. That is my new data set. And from that, I calculate my new estimation of the standard deviation. And if I now going to use the central limit theorem, this means that I now have done 10,000 experiments. So that number m is 10,000. So when you think back to what we did, we should actually get a standard deviation now, which is the original one, 15 divided by 10,000. Okay? So I would have gotten the same result if I had generated 10,000 points 10,000 times. You can actually check that. But what I'm doing now is to apply the bootstrap, which in essence does the same as you generating the points. In this particular case, doing the bootstrap is going to be a little bit quicker than actually calling a Gaussian and to generate 10,000 points 10,000 times. So that tells you already. So I leave that as a kind of exercise to you guys to actually look at that, replace what I've done with the bootstrap, and call the Gaussian distribution 10,000 times and generate 10,000 points. And you see now from the distribution which I'm getting, and this is the interesting thing here, is that when I do this, you get 15 divided by 100, which is now roughly 0.15. You see the mean value is essentially the same, and you see the distribution here around the mean value. So I could do this 100,000 times, and then I would clearly get this divided by the square root of 100,000, and I can keep going on like this. So this is just a demonstration of the central limit theorem. And applying the bootstrap is in this case the same as you generating 10,000 data sets again and again. And you see now why the bootstrap, you can actually show that, and I'm not proving that for you in the lectures here, but you can actually find proofs of the bootstrap theorem that you do actually approach the correct standard deviation in the limit of many, many bootstrap experiments. And for identically distributed and independent variables, this is actually what takes place. So you see what you're doing now is you are narrowing down the distribution. You would have gotten the same result if you had taken 10,000 times 10,000 points. That's 10,000 samples. The same standard deviation and the same mean value. Okay? So it's a very good method when you don't have much data. And this is where it's typically used. So the method which is the choice for this type of calculations which we are doing is one which is better suited for millions and millions of observations. And this is something which we can typically generate when we run one of these Monte Carlo calculations. And this is the blocking method. So in order to do the blocking method, we need to do some additional, we need to introduce some additional quantities. And I see that time is running a little bit out. So instead of beginning with a new topic, because we have only some 10 minutes left, so I suggest that I'm going to prove for you and show you the blocking method next Friday. And then we will also discuss parallelization, because I would need something like half an hour, 40 minutes to demonstrate that. So I hope it's okay if we don't jump into a new topic, but that we stop with a bootstrap. You have the codes if you just want to use them as a post-analysis. And I normally recommend to actually do the post-analysis after the big calculation, especially if you run a huge and lengthy calculation. Then to run these post-analysis things is something which is normally not very time-consuming. And you could run the analysis both with the bootstrap and the blocking method, and then compare the two types of standard deviation which you get. So the bootstrap method, just to remind you quickly of what that will give you, is the following. So let's just go back to the central limit theorem. When we use the bootstrap so the bootstrap also comes in terms of a variant for variables which are not identically distributed. But in our case, what we will have with the codes which you have access to online here, is that you will find a standard deviation which looks like that. And for your Monte Carlo calculation, you will see that the blocking method, which takes into account the fact that there are correlations between the observations, will give you a standard deviation which is slightly larger. And then you may ask, why should I worry? Why should I care about the 10 to the minus 4 and 10 to the minus 5? You can simply assume that everything is independent and identically distributed and live happily forever with that. But we are normally a little bit more picky customers. And then we would like to have a more precise estimate, especially since we know that there most likely are correlations between the different measurements. And then the standard deviation will not be as small as we would get from the central limit theorem. But this is a typical thing you will observe many, many times. And feel free to play around with the, you can replace the Gaussian distribution with a Poisson distribution, or any other distribution where the particles are assumed or the observations are assumed to be independent and identically distributed. And then your distribution will always approach a Gaussian in the limit of many, many measurements. So that example which I showed you is something which you can play around with other types of distributions, the initial one. So I just assumed that everything was distributed according to Gaussian. I did 10,000, produced 10,000 events, and then I did the bootstrapping 10,000 times, which in principle is a way to generate 10 to the 8 events. Any questions so far?